Okay, so so we're welcome to the 34th episode of SFU Sports Analytics Virtual Seminar Series. Today we have Robin Ritchie, Alon Bell, and Phil Shreves to speak to us about passive evaluation ice hockey. The speakers are graduate students at Simon Fraser University who all share a passion for sports analytics and talk about today submitted to the 22 Stathletes, and they won that competition. So yet another trophy for the excellent students here at SFU Sports Analytics. So Robin's a PhD candidate in statistics, and she's co-supervised by Dr. Tom Logan and Dr. Alex LeBlanc at the University of Manitoba. Alon Morel is a PhD candidate in engineering science and supervised by Dr. Ivan Bajic. Phil Shreves is a PhD candidate also in statistics and supervised by Dr. Bingham. So in terms of what they're going to talk about, discuss the development and deployment of a framework for evaluating passing in women's ice hockey. So they used event tracking data collected directly from broadcast video games of the 2022 Winter Olympics. They will describe a physics-based motion models for the player and the puck, which they used to develop a model of probabilistic passing. Next, they modeled rink control for each team, the scoring probability of the offensive team. Models were then combined into novel metrics for quantifying the various aspects of any single pass. Looking at the entire corpus of play, several summary metrics describing players' risk-reward tendencies and overall passing were evaluated. So this is our talk that we haven't, our first talk in a long time. We're really looking forward to it, and I'm going to turn it over to you, Alon, to share your screen.
Will do. All right, hi everyone. I was going to do a little bit of introduction, but Dave took care of that. So let's jump right into it. So we want to talk about a little bit about the goals of what we were trying to achieve here, like what we're coming for. So there's not a lot of tracking data in women's hockey. So this event was a great opportunity to get some and try to use it to give some meaningful insight. We chose to evaluate passing because we think that's a very meaningful aspect of hockey, and specifically one that we could evaluate quite well as well. And we wanted to do it in a way that gives actionable metrics, gives things that coaches or players or scouts can relate to easily, can understand relatively simply, and then they can use it in a variety of different ways, whether it be with video, with lineup choices, or with actual scouting and choosing the which players to bring to the team. So yeah, as I said, in general, player tracking data is often collected by proprietary collection systems that are very, very expensive, and the result of their high price and also the fact that they, the competitive edge that they bring, that data is generally not made public. However, recent advances in computer vision have made it more possible to collect tracking data directly from broadcast video, which is generally speaking publicly available. Sometimes you have to pay for a subscription or a specific channel, but the video is generally publicly available. And it's the development of this technology is particularly useful for sports that are generally underserved, underfunded, whether it's lower level leagues, amateur level sports like hockey, college level, or high school level, or in our case, women's hockey, which is unfortunately underserved as well. So as a result of the kind of lack of data, there's very little public research in women's ice hockey, and as far as we could tell, not a lot of private research either. And the little that there is generally driven by competitions such as this Big Data Cup that we attended to, that I'll expand about in a minute. And even so, a lot of the research that is out there uses more event data, which is less fine-grained than tracking data. So we were hoping to change that a little bit. So just talking a little bit about the Big Data Cup, it was sponsored by Stathletes and a group of universities and partners. They provided broadcast video tracking data from the 2022 Winter Olympics women's ice hockey elimination games, specifically from power play and penalty kill situations over 6 games. So we got a total of 37 power plays. We also need to shout out the Bucket List, who helped clean the data and made his clean data public, which was a big help. So the data did consist also of event data. So event data is, as we should mostly be familiar with, it's sparse over time. It just happens when an event occurs. There's things like shots, passes, goals, that kind of thing. And for each event, you have a list of attributes like who's involved, what's the score, what's the time, things like that. But it's not very fine grained or regular. And on the flip side, there's broadcast data, which was provided at 30 frames per second. It was done only from the broadcast video, from the main camera. So that means it's a bit intermittent, and at times there's splits and like you lose the tracking data entirely, and then you get it back. And of course, because it's broadcast video based, and broadcast video does not show the entire ice, then there'll be players coming in and out of the camera view occasionally. But nonetheless, you get at 30 frames per second a list of the locations of all the players currently visible on the ice. So we're gonna use a specific play to kind of demonstrate how our method works and what we've done. And we're gonna use this play, which is from the Finland versus Switzerland bronze medal match, and it's a goal for Finland that starts with a pass from number 33 to number 16. Number 16 loses the puck and then regains possession before passing back to number 33, who shoots, and she scores. So we'll use this play in a lot of our demonstrations, and note that we're only doing pass calculations when someone currently has the puck, and we're showing these GIFs at half speed because otherwise hockey's quite fast. All right, so before we jump into the details, let's break down how we approach pass evaluation. So first thing we wanted to do is understand how players move and how the puck moves. So we use physics-based models for that. And we account for things like friction, reaction times, and stuff like that, and we'll get into the details of those very shortly. After that, we wanted to give value to different points of the ice. Obviously, where you are on the ice matters as far as whether or not someone wants to pass to you. So we wanted to do that, and we wanted to make sure we're accounting for where the defense is, where the offense is at a given time, so not just kind of a naive approach. After that, we wanted to model the actual passing. So what's the chance of a team receiving, like an offensive player receiving the puck at different spots, and what's the chance of it getting intercepted along the way? Okay, so now we have all these three kind of building blocks. We were able to go on and make metrics, and we started by using frame-by-frame metrics. We wanted them to be useful for analysis of the different aspects of the pass at different times. Specifically, the frame-by-frame metrics are kind of used alongside video so that you can kind of see what's going on. And finally, and I think most importantly, we took these frame-by-frame metrics and we used them to try and make a broader understanding about players' decision-making and how they pass and their overall capability and stuff like that. And we'll jump into the details right now.
Yeah, so movement in hockey is quite complex. And so the first thing that we needed to do before moving on to modeling and passing is modeling the player motion. So we'll start with the player motion models, and that can be seen as an example in the top right. Here, what happens is that the players are going to accelerate against a resistive force, which is going to lead to a predetermined maximum speed. So this is characterized by our two equations there. And if we take a look back to the top right, you can see that if a player starts in the origin, moving right along the x-axis, then anywhere inside that circle is a possible point that they can reach within 1 second of time. We're also sure to add a reaction time of 0.189 seconds, during which the skater is going to be able to continue along their current trajectory before moving on to changing direction. We can then model the puck motion. And the puck motion is going to move using friction and Stokes drag, leading to the following formulas with the relevant physical coefficients. So using this, we're going to consider many possible passing angles and speeds as well. So if you take a look at the bottom right there, we have a number of dotted lines, which are considered multiple different passes that a player can make. Each of these passes has a set of triplets along with them. So if you take a look at each point on the ice, each little X there in the bottom right, one of those is considered a possible location time triplet. That being said, it contains 3 possible points. So it's got the position, which is the X and Y values, as well as the time it takes for the puck to get to that position. So note that we'll be referring to either triplets or location throughout, but either of the two are one of these points in the bottom right there. We can then move on to valuing the ice. And doing so, we're going to begin with our what we call a naive scoring probability. which is simply based on the proximity to the goal as well as the angle. So we start with modeling the proximity to the goal, which is just a simple squared exponential function displayed in the first line of our equation there. So that just takes into consideration that if you're further away from the goal, it's harder to score, and if you're closer, it becomes a bit easier. We then also take into consideration the angle with respect to the goal, which is shown on the second line of this equation. So, for example, if you're quite close to the goal line, it's going to be harder to score than, for example, if you're straight on. Now, note that this does not take into account defensive pressure. And if we want to do so, we can move on to our next slide. So here, we're going to use what we refer to as rink control. So this was inspired by a soccer application. And what it's going to do is account for the offensive presence and the defensive pressure on the ice. And so it actually comes originally from a physics application. So it treats the players as if they're moving particles. And it uses their presence to measure the total value of the field at a specific point on the ice. So you can see that we have darker areas. Those areas are going to be areas that are controlled by a team. The lighter areas, the areas that are in white, are areas that are up for contention. So if you were to pass somewhere along a white area, that's an area that's up for grabs.
Okay, so now that we have a motion model for the players and the puck, we want to figure out which, at all those time triplets on the ice, who's going to be able to get to those locations first to be able to pick up the puck. So we start with a base pickup probability. So if we want to calculate this, we can look at a given target. So we'll say the target is the star, the puck location, wherever the puck is going to be after a certain amount of time. So we'll introduce these as the base pickup probabilities. So imagine a player is attempting a pass to a target location shown by the star. If we wanted to determine the player's order of arrival at that specific target, we can do that by looking at the time it takes the puck to arrive there. So if the puck takes 2 seconds to arrive at that point, we're going to take all the players who might be able to pick up that puck. They're going to continue in their current direction for their reaction time and then converge on the target, the puck location. We can note that the reaction time is slightly different for the offense and the defensive players because we assume that the offense is able to anticipate a puck or a pass where a defensive player might be reacting more in a sense. So by the time the puck arrives to that location, each player who is able to converge on that target is going to have a distance dij, so how close they actually got to that specific point. So we assume that players have a reach and thus a likelihood of reception that's based on a Gaussian distribution that's scaled by the average player's reach, which we take to be about 6.5 feet, just based on how we think a woman's height might be and how far her stick might be able to reach. So if a player can reach in one length in either direction, the overlap between the blue section that we have here on the curve and the curve is the probability that a player is going to be able to pick up the puck if the puck is there when they are able to get to that location. So we can note that this is a per time interval, since a player can often have multiple chances at controlling the puck. Again, this one's a little bit more of a visual. So if we want to look at that exact time triplet, we see how the puck is going to take to get to that star, converge all the other players onto that target, get their distance dij, and then their base probability is a function of the dij. And then what we want to do is remove the conditions on this. So right now it's conditioned on the puck being there when it arrives and you being the first player to get there, which isn't very realistic, right? So we want to be able to condition on the order of arrival as well as the trajectory of the puck. So we're first going to start with removing the order of arrival. So whoever is able to get to the puck first is going to have the highest chance of collecting the puck. And then the second person to arrive is conditional on the first person missing collecting the puck, and so on. So it works like that to account for order of arrival at every single target. So then we can sum over the offensive probabilities, which is what we saw in the figure there. And then what we want to do is remove the condition on the puck arriving to the target. So the trajectory that the puck takes needs to be taken into account. If there's a higher likelihood of the puck being picked up close to where the pass originated, then each point further along needs to take that into consideration. So we do that by essentially just calculating the same thing. We calculate the base probabilities at each of those time triplets, and then we remove the condition on the order of arrival, and then each point, similarly, we remove the condition for each point that follows in order to update these probabilities, and then those are our final passing or reception probabilities for each player, and we can see what's going to happen. So then what we want to do is look at which angles are going to be likely to have success, right? So we want to see which passing angles are most likely to be picked up by one of your teammates somewhere along that trajectory. So what we do, what we just saw on the last slide, we take the sum of these probabilities for the offensive team along the trajectory to get an idea of the chance of success, given the speed and angle of the pass. So this metric tells the passer which passing angles, given that speed, are safest and will likely be picked up by a teammate somewhere along the way. Then we could freeze the frame. So what we see here is as number 40 on the very right side or left side enters the offensive zone, she's immediately highlighted by our metric. As there are no Swiss players around her, she is identified as a player that will likely receive and control the puck if number 16 passes towards her. Number 33 on the right is also a good second option, but there's a high likelihood of interception just to the right of number 16, so it takes a little bit of a hit on that condition. So we can see which passes are ideal and not as ideal, just looking straight at who's going to be able to receive the puck. So this is a useful tool for players and coaches when reviewing any play alongside game video. And we can equally do the summary for the defensive team to see where the highest areas are for interceptions. All right, so before using our passing model any further, we want to evaluate it in a real game scenario. So on the left, we have the successful pass probability for the success versus failed passes. And on the right, we have our ROC curve for our estimate as a predictor. So using both methods, we can see that our model highlights the angles which are most likely to be received by a teammate and separates with good performance between successful and failed passes.
So now that we've developed our passing model, we can move on to some actionable metrics. We're going to start with location value, which is going to define how much potential any one point on the ice has. And how we do that is we take into consideration not only the probability of scoring at a given point, but also the rink control, how much our team is going to control the ice at that point. This is going to be used to quantify high value areas for the offensive team of interest, where they might want to pass to, and where the defense is going to want to keep the offense away from. We can then move on to our conditional location value. And so the conditional location value is a metric that's going to incorporate the team's rink control and scoring probability, but then it's also going to take into consideration how likely it is that your team is going to receive the puck at that point. Note that this conditions on the fact that the puck gets to that point. If we wanted to take into consideration interceptions, for example, we can move on to what we call our location pass value. The location pass value is quite similar to the conditional pass value, but here we actually require the puck to successfully reach the desired point, removing the previous condition that we had. In doing so, we're now accounting for potential interceptions along the way as well, and accounting for the probability of a teammate receiving the puck, the rink control, and their scoring probabilities.
Okay, so moving forward, we have our best case pass value. And what this tries to do is to say, what's the optimal kind of value of a pass if I am able to get it through. So the way we do that, we take the maximum of our conditional location value, which Phil just described, and we do that over an entire pass trajectory. And the reason we choose the maximum here is because we want to say, okay, if I were to get the pass through, if I got lucky and managed to squeeze the pass all the way through, how valuable could it be? And essentially, it's a measure of the possible reward of a pass without taking into account the risks, which is going to be useful later when we try and analyze a little bit of players' risk-reward tendencies. So if we, again, freezing this frame over here, we see that number 16 has a number of possible passes, but interestingly, the spot right in front of player 24, and this is a good example to see how the speeds are incorporated, that the best pass is not to number 24, but rather a little bit in front of her. And we see that that pass, if number 16 were able to thread the needle and get the pass over to number 24, then that will be a very high chance to score because it's very close to the goal, obviously. However, this doesn't take into account for interceptions, and we could imagine that making that pass from 16 to 24 is going to be very, very challenging. And so we were going to want to account for that later somehow. So as we said before, we also took metrics that accounted for the entire kind of value of the pass, the trajectory. We accounted for interceptions and receptions and value of the ice and everything all together, and we called that the location pass value. And then by summarizing over that for the entire trajectory, and this time we're summing because these things now take into account the likelihood that the puck even got to the next spot. So by summing over that over the entire trajectory of our pass, we get what we call the expected pass value, which, as far as we can do, is the most comprehensive evaluation of a single pass at a single velocity and a single angle, accounting for all different aspects that go into making such a pass. And once again, we're going to freeze the frame at a similar spot to where we did before, and at the previous frame when we talked about successful pass probability. And if we remember from there, what we saw is that number 40 was highlighted as kind of the safest pass, the highest likelihood. But we see here that when we're trying to account for the value of the pass, number 33 is located in a much more dangerous spot. And so passing to number 33, as opposed to number 40, all of a sudden becomes highlighted by this metric because it is kind of close to being as safe as number 40, but it's much more valuable. So this makes the pass to number 33 the preferred one. And that, in fact, was a pass that was made in the game, and even more so, it led to the goal. So that's a good sign that our metric kind of identifies this as the best pass. Now that we have our individual kind of frame-by-frame metrics that evaluate each step along the pass, we wanted to say, okay, how can we evaluate players as a whole, their passing capabilities or tendencies or behaviors as a whole? So we start by this graph, which we refer to as the decision-making graph. And what we see here going up is the average best case pass value. So if you remember, best case pass value is kind of a measure of a reward without accounting for risk. And so the going up, this graph means the players made passes that were of potential high value. They made passes that if they made it through, they would be very, very good. They would be increase the chance of scoring for the offense. As we go further to the right, we are seeing the average successful pass probability. And that's, in other words, to say how safe were these passes that these players chose to make. How likely was a teammate to receive the puck on average when this player made a pass? and that gives us kind of these four quadrants. So obviously being in this kind of pale green area on the top right is optimal, is the best case. But importantly, we can kind of differentiate the two other quarters. And while a coach might be more inclined to play players up in this area, the aggressive kind of gunslinger type players that go for the dangerous passes, they may not have the highest successful probability, but they're going to be very valuable. So you might be more inclined to play these players when you're down and you're trying to score urgently. On the other hand, if you're leading and you're trying to maintain a lead, you might go for these players in this yellow quadrant down here because they are more safe. They try to keep control of the puck, even if it doesn't add too much value their passes. Now, I want to just say a little thing about everything I just said and qualify it and say that this is a pretty small sample size. We're talking about 36 total power plays, about 250, I think, passes made it through after filtering for good data and all that. And so this graph has a minimum of 3 passes per player. So it's much more likely that players like Nelly Leitonen belong here in the top right, 21 passes, than it is that Hannah Brandt belongs in the red here with her 3 passes. So please take that with a grain of salt when evaluating these actual specific players.
Okay, we can then move on to evaluating the overall passer performance as well. And we do so using the scatter plot, which plots the best outcome as opposed to the relative outcome. So we quantify the best outcome by considering the value of the optimal choice. So what we do is we take the maximum over the expected pass value of many different options. So we consider all possible passing angles as well as 4 different speeds. We also consider the possibility that the player just simply holds the puck and decides not to pass at all. The relative outcome is going to be the expected pass value of the actual play compared to the optimal play. So if we look to the plot on the right, you can consider moving further right along the plot as putting yourself or having your teammates putting themselves in a better position to pass or receive the puck. The relative outcome, on the other hand, moving further up on the plot, may be considered how well these players are capitalizing on their opportunities. And so, as you can see, if we move into the top right there are many Canadians who are in the top right, which means that they are, in fact, likely positioning themselves quite well in order to pass and receive passes, and they're making the most of their opportunities.
And I think it's nice to say that this probably paid off for them quite well because they won the gold medal in this tournament.
Yes, yeah, exactly. Okay, so then we can move on to recap. And what we've done so far is we've used publicly available data and developed some novel metrics. So specifically, we've developed the successful pass probability. We've developed the best case pass value and the expected pass value. So those are our main 3. And these can be used for a multitude of ways. So specifically, the players and the coaches can use these in film studies. The coaches can use it for decision-making, for what kind of lineup choices that they want to use. So as Alon said, if you're down, you may want to choose some of the more aggressive gunslingers. If you're up, you may want to use some of the more conservative players. And the scouts can use it for roster construction. You know, where are they missing? Where do they have holes in their roster? What kind of players do they want to pick for the future?
So this we do have another little section coming up soon, but this is a good point to pause for a few questions about kind of the main portion before we move on to the next bit. So if anyone has any questions and anything they would like us to go back to, then we would love to do that now for a second or a while.
If you have a question, just unmute and ask away. So maybe I'll ask one now. So if I understand correctly, I probably have to read for a few times to grasp it, but your algorithm tends to value like the next pass, but what about like set plays where, or power plays, like they're passing the puck around initially to try to find gaps and like that. So how does that get figured in?
So it doesn't get kind of referred to directly in a sense, but I think what will happen with those kind of passes where you kind of passing the puck around the formation of the defense is that you'll end up with passes that have a comparable value on the ice. So like the pass isn't really contributing much value, but they'll be very safe, right? Those are passes where the chances of completion is going to be pretty high because you're generally like the defense is kind of in a smaller cluster closer to the net, and the offense is kind of moving the puck around, trying to find, you know, where the gap in the formation might be, and they're doing that relatively with safe passes, right? So I think those kind of passes will be highlighted by our metrics in the sense of high probability, but they will be probably a little bit lower value. And so if we kind of go back to our kind of decision-making passes, those are probably going to be passes that are around here. Sorry, lost my mouse. Around here. And you know, building on that, eventually in that kind of situation where the players are passing around, eventually someone's going to try and make that pass, thread that needle, right? That's otherwise you're just kind of wasting your power play. And if they do that very, very well, they'll be up here. And if they do that, you know, mild performance, they might be up here. But the idea is after a bunch of these passes, you got to make one of these passes.
So yeah, and one of our main end goals was kind of to build like a being able to chain passes along and see like if you pass here, then you could pass here. But then it's like where the players move, you have to model where they're going to be in that many seconds and all that, and it gets really complicated as sports does and hockey does.
Yeah,
Yeah.
well, yeah, I can imagine. Just while you're on this slide, and Tom, I'll get to you in a sec. Like how meaningful, in a sense, is the distinction between players? Like, like a difference in best case value from 0.0 to 0.08. Like, what does that mean functionally? Can you tell, like, these are players here, skill levels are noticeably distinct, by coaches and whatnot.
So sorry, Dave, it was a little hard to hear you. Kind of broke up a little bit there.
Oh, sorry. You can hear me a bit better now. Just on that previous slide, like your player summary slide, like you have these plot and there's numbers on y-axis for like, what is the meaningfulness of those numbers in terms of like, would I definitely want to pick Melody Daou over Aaron Ambrose or vice versa on what I'm looking at, or how distinguishable are these players based on these numbers?
Yeah, so I guess he's asking about the axis. So just like for the successful pass probability, right? It's always, I think we range it between 0 and 1.
Yeah,
so it's basically like a guaranteed. Yeah, a 1 would be like a guaranteed pass based on our motion models. And then for best case pass value, it kind of is a probability multiplied by probability, and they can get pretty small. So they don't tend to have very high ranges because they are risky plays and risky passes. So there might not be like a huge difference necessarily between like a small degree of difference in either one. But I guess just like for an overall sense, like you'd want to pick, like if we would imagine it, if you're building your lineup, you'd want like someone from the yellow zone and someone from the purple zone just to have like a good contrast of players on the ice. But again, it's also like opportunity, right, is behind each of these things. So maybe you only have a good successful pass available to you and you don't have a best case pass available to you at that time. We also wanted to look into like positioning. So my hunch would be that a lot of the people in the yellow are actually the defense, and a lot of people in the purple are probably the centers. So looking at the defense compared to a lot of these, I think would also give a good insight into which players should be on the ice.
Yeah, and just to add on a little bit, the best case pass value, if I'm not mistaken, is the maximum conditional location value along a certain trajectory. So basically, if you can just thread the needle down a certain line, what is the best case scenario? So for example, you said, comparing Nelly Laitinen to Aaron Ambrose, should we play one or the other? A difference, for example, of 0.01 in best case pass value, you're more likely probably you want to have that extra 20% in a successful pass probability, I would say.
Yeah, and I'll take Phil's answer one more step and say that hockey, like say football or the round football, is a very like the reward is infrequent. Like there's only a few goals a game and many passes, and so it's kind of expected that the value of a single pass is generally speaking quite low. And so a small difference here actually could represent a big difference in game results and effect on game results. And that was something that we would really like to quantify if we had a bit more data, like how these passes then translate into actual game value.
Okay, thank you for that. I'll go to Tom and then Paul. I see your hands up. We'll go to you after Tom. Go ahead.
Thanks. So far, it's been great. Looking forward to the second third of it, or whatever you want to call it. Right now, if I understand correctly, and please correct me if I'm wrong, your model so far is talking about the value of a pass, assuming that a pass is going to be made, as opposed to whether a pass should be made. Is that right? I mean, it doesn't evaluate whether the player's position on the ice presently is better than the one they would want to pass to.
In one of our metrics, the relative outcome or best outcome, one of them. It compares like the best pass, but we also account for the location where the player is standing. So it's should you have held the puck or passed. So we do consider that in this table. Ideally, like we did want to also include like a time step of should you have passed a second before or a second after. Multiple levels of complexity can be added.
Yeah,
Right,
and also,
right.
for example, like if I'll take from what Robin said, we're not accounting, for example, of you carrying the puck. That might be a better alternative too. You could shoot. Like if you look at, if I go back to sort of this slide, or this slide even better, number 16 at some point is going to get the puck, or sorry, number 33 is going to get the puck where she's about to score. And if you look at our metric is kind of telling her to pass it backwards. Right, but she actually scored. So right there, so it's obviously not accounting for all like alternatives. It's just referring to a different pass, and we would very much like to eventually maybe include carries and like
build an
Robin said,
expected
future
threat
passes.
model.
Yeah, future passes and past passes, alternatives to say like was this player doing the right thing overall? But right now it's just on the actual like if they passed, was it a good idea?
Mm-hmm.
Sure.
And a way we can do that is, sorry, Tom, is that we have all of these metrics in place at the moment. We have the value of considering holding the puck. We have our expected pass values, and we also have scoring probabilities. So we could do that is finding ways to compare these three metrics all at once and say, okay, what is the best possible thing we can do in this scenario?
Right. So it's a very compound decision-making problem, many different decisions to be made, and you're focusing now mostly on one of them, but there's lots more to go. Great. Thanks very much.
Yeah, thank you. It's a really interesting approach to this topic. You mentioned how you want to get more data in order to continue the refinements of these, and I love the fact that you're thinking ahead to what's the practical application as opposed to this being a interesting theoretical exercise. I'm curious how long it takes for the computer vision to digitize a game or even a period, I guess, to get those data that you were required to do this, and then in the future to provide the feedback to coaches, let's say in a tournament.
Yeah, the tracking data is all provided by Stathletes. So it's Pascal and Megan Cheka who gave us all the data. So we just take the tracking data and we can do our computations. We did actually work recently, and Alon was able to get everything down to extremely fast. So you'll see in our next section, we'll show a little bit more detail about it.
Okay.
Yeah, so if taking that like a little bit, so CV models are they're getting better and faster. So that's kind of not the main focus of this work, but it's kind of related to stuff that I do on as my in my main PhD, so I can answer that. We're getting very close to real time tracking from video right now. The issues become more about the data cleaning and fidelity, because what you get is scenarios where you lose a player or you lose track of who that player might be because you can't see her jersey number or something like that. So the actual processing is not so much the bottleneck. We got our model down to depending on what platform you're running it on, but we got our model down to run in 30 milliseconds, give or take, which is enough to run this close to real time, right? So the issue, and the CV models are also comparably quick. The main issue is making sure that the tracking that you get from the computer vision is actually matching the player IDs and stuff like that. That's kind of currently the thing stopping this from being something you could implement live in a game tomorrow.
Yeah. Thanks.
Okay, I think with that we'll keep going. So we're gonna change gears just a little bit. We're going to highlight one of the other entries into the Big Data Cup. So this was done by the team of Carly, Ben, Ann, and Nan, who created the Highway to the Danger Zone, which is an interactive. Their project looked at algorithms related to star formations in order to look at connections between players and evaluate danger. So given the power play formations, the penalty kill formations, how dangerous of a situation is it to lead to a goal. So they built an interactive web tool, which allowed you to move players around and see a threat forming, or a threat in a formation that could potentially happen. So we really liked their app. We really liked our visuals. So we thought that we could, build the ultimate team up. So what we did is we got in contact with them. And then using our visuals and their tool, we created women's hockey evaluation of the play, also known as We Play. So it's an interactive tool to evaluate passing and assess danger. So we combined our metrics with some of theirs to update their danger model also. Can you restart the video, Alon?
I don't know if I can, but I'll try. There we go.
Okay, so you can select the number of players. You can also, on the offense or the defensive team, and change that all around with our app. You can click and drag players around to see the metrics update in live real time. So right now it's on our rink control. Or alternatively, if you want to make a lot of changes and move a lot of players around, things can kind of get a little bit laggy. So what you can do is you can toggle run models automatically off and then make as many changes as you want. Everything's going to stay completely the same until you rerun the models, in which it will update it for you. So we'll rerun the model. We changed it.
Sorry to interrupt, but super cool. But do you have velocities associated with these players? Directions?
For this app, we don't. We start them at stationary and then we build them to be able to accelerate.
So as a ice sport coach, I'm just looking at I'm drooling at this to see how I can subtly change my players' position.
Yeah, so that's really the goal, is we wanted you to be able to look at rink control, look at successful pass probability, best case pass value, expected pass value, and then it also gives a danger evaluation on the play. So a coach ideally can use this to show their team certain formations where they were, or you can take it home to your beer league and show it to your friend and say, I was open, this was our formation, why didn't you pass to me? So it's multi-use. So as you update and move, the danger is going to change from sometimes there's slight danger. So we defined a dangerous situation as either you have an unblocked shot on net, or someone you could easily pass to has an unblocked shot on net. So there's two kind of scenarios that we consider there.
And I might add that this app is available for everyone online at weplay.netlify.app, and there'll be a QR code at the end if you want to take a screenshot towards the end of the QR code or of the URL right now. And we take pride in the fact that this works basically on any device. You can do this on your mobile phone. And of course, it'll be a little bit faster if you run it on a high-powered PC, but it will run on whatever you have.
Yeah, and it takes a little second to load, but it's doing a lot of information in there.
Yeah. If you're doing it on your mobile, please allow it about 15 seconds or something to initially load the app, give or take. After that, it'll run pretty quickly.
Yeah. Okay. So we wanted to highlight just a couple of scenarios that are just common hockey power play and penalty kill formations to be able to see how our metrics react. So first we have a 2-on-2 power play against a 2-2 box penalty kill. So we'll point out here the successful pass probability in the bottom left highlights 2 passes which are likely to maintain possession. So these ones account for acceleration in the direction of the pass and not being intercepted anywhere along the way. So if you pass to those high blue areas in the bottom left, those are really the safest passes if you want to maintain possession. Moving on to the next slide. So next we have the same power play formation, but this time against a triangle +1 penalty kill. So here we can highlight the expected pass would likely be to player number 3. So she's in a good spot to receive the puck as well as in a decent position to be able to shoot. We can note that it does kind of take into account that you're able, so we don't really have directional information. So sure, this is a good pass, but then number 3 would have to receive the puck and maybe turn around in order to shoot. So we don't really have the rotation aspect, I think, included in our model. So that would be something we'd like to add. And then finally, we have a 1-3-1 power play against a triangle +1 penalty kill. So we'll highlight here the best case, which is in the top right, which shows that player number 4 is in a valuable position. So if we were desperate for a goal, threading the needle to her may give you a good scoring opportunity. So there's a lot of danger involved, as it's probably a high likelihood of interception. But if you really were desperate, you could pass it super hard. Maybe number 4 would be able to one-time it right into the net. So, right, this could be used for video coaches at the game level, on an iPad at the game position, be able to consider all kinds of different positions of what's going on. Ideally, one day, maybe it could be a filter on an app that goes over the live video, but we'll see where we go with this. Yeah, so here's the QR code to our web app, as well as the GitHub for our original project, which has our paper in there as well. Yeah, so thank you.
Awesome. Thank you very much.
I could put the link in the chat. Maybe that will be helpful.
Okay, so I'll start off the question. So you think this will be useful for beer league players to ask why they didn't play? So do you have a part of this app that assesses the danger of a fight in the parking lot after the game?
Not quite, no.
I mean,
Okay.
depending on which team you are.
I'll open it up to serious questions now. Don't be shy.
Yeah, so we made the app and presented at CHAC with Anne, Carly, Ben, and Ann.
I guess all the questions were asked in the first
Yeah.
section.
May I please ask a question?
Sure.
Yeah.
Or two. So I think we talked about this at one point along, but is there thought? Well, is it reasonably difficult to include like common plays of bouncing the puck along the boards or wrapping it around the boards? That's a standard pass.
We looked into that. The difficulty is that we don't have, first of all, we don't have a lot of passes that were made like that. So it would be hard to evaluate how our model kind of relates to that. As far as doing the actual calculation, we looked into that as considering if I go back to, actually, let me do that. If we looked at these trajectories, sorry, I had to go way back. If we look at these trajectories, they all end at the boards, and we thought about extending them and then reflecting them off the boards to account for like a bounce pass, or sliding along the boards kind of pass. The math isn't trivial. There's especially for multiple bounces. There's some work on this that was done as part of the another hockey analytics conference, which the RINHAC, I believe it was called RINHAC or RISHAC. And they took one bounce at most. Anything above one bounce, the math becomes incredibly complicated.
No worries. Just thought I would mention it. I know I've asked you before, but
yeah, we looked into that. We actually have code that does the one bounce, I think, but we just didn't have enough plays to really make it worth putting into the main model.
Totally. And then one more thing related to valuing the ice. Is there any way to model? So yes, we care about the value of the ice in terms of attacking power, but is oftentimes in an offensive opportunity that if you make a bad pass at a certain point, you can cause like a breakaway, and then the opposite occurs. Is there any way to kind of model like the?
Yeah, we thought about that a lot too, about like the value of an interception, kind of the negative value of an interception. It's obviously different according to where it happens. And also, like, you can take that further and say, like, any pass behind, like passing behind the blue line is is almost negative value, right? Because you have to then reset. Your entire team has to kind of go back behind the blue line so you're not offside. So yeah, for sure, there's ways to make our like valuing of the ice a bit account for like the downside of passing, not just the plus side of passing, for sure. Yeah, we thought about that. Again, I'm not exactly. I can't remember exactly why we didn't incorporate it in the model in the end, but yeah, that's definitely a thing you could consider.
All right, cool. Thanks for the answers.
Thanks for the questions, Tim. Anyone else? Okay, well, maybe at this point I'll just let's thank the speakers one more time. Then maybe I'll shut down the recording. Have some informal chat. So yeah, thanks very much again, Robin, Alon, and Phil. Congratulations again on your cup win. So I'm just going to shut down the recording and I'll open it up for formal discussion. Take care.